Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptix podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to explore why deep learning suddenly took off after decades of slow progress and what finally made it succeed.
It's a great question. And it's one of the most compelling stories in modern tech, really, because the shift was just so incredibly rapid.
It felt like it came out of nowhere.
It really did. Today, artificial intelligence applications, everything from computer vision in your phone to natural language processing that powers translation.
All the generative text models we see now.
Exactly. They're almost entirely reliant on deep learning. It's become the definitive engine of modern AI.
That's a good way to put it. For most of us who weren't, deeply embedded in computer science research back in the 90s, the speed of it all just felt like a lightning strike. One moment, AI seemed kind of stuck, and the next, suddenly in the early 2010s, we have these dazzling image recognition breakthroughs, and now we have models that can generate human-level text and even code. But here's the central mystery, the thing we really need to tackle. The fundamental concepts behind these artificial neural networks, or ANNs, they aren't new at all.
That is the paradox, isn't it?
Yeah.
The core architectural ideas, this whole concept of modeling learning as a structure of interconnected nodes, like the brain, that dates back 70 or 80 years.
So if the foundational theory was that old, why did this spectacular global success only happen so recently?
The answer, and this is what we'll get into, is that it wasn't one single grand invention. It was a massive convergence. It required the simultaneous alignment of really three critical pillars: algorithms, data, and computation.
Okay, let's unpack this. And I think we have to start with the periods where the field really struggled, the infamous AI winters that plagued all that early research.
To understand the modern breakthrough, you absolutely need that historical context. The beginning is rooted in a philosophy called connectionism.
Connectionism.
The idea was simple, but pretty profound. The mind is made up of interconnected elements, and learning happens by changing the strength of the connections between them.
So researchers weren't just trying to solve, say, one specific problem. They were trying to build systems that learn the way a brain does, or at least a highly simplified model of one.
Precisely. And the theoretical foundation was established very early on. Back in 1943, McCulloch and Pitts introduced a formal model showing that if you combined simple theoretical neurons, these little elements that operated with basic logic like ANDs, or Rs, nots, you could build a system capable of universal computation.
A Turing machine.
A Turing machine, exactly. So this demonstrated that the concept was at least mathematically sound.
Okay, so the theory was there. But how did they make those theoretical neurons actually, learn?
That piece of the puzzle came shortly after, in 1949, with Donald Hebb and what's called the Hebbian learning rule. While McCulloch and Pitts showed what the network could do, Hebb proposed how it would change.
Okay.
He laid the groundwork for this idea of associative learning, suggesting that when one neuron repeatedly helps to fire another, the connection between them gets stronger. The famous phrase is, neurons that fire together wire together.
Right. I've heard that. So that was the conceptual engine for learning.
It was. Then we get to the late 1950s, which introduced something more practical: Rosenblatt's perceptron. This is often cited as the first functional network model.
And what made it so practical?
Well, the perceptron, this was in 1958, was a crucial step forward. It took those theoretical ideas and built a machine that could actually process real valued inputs, not just, Boolean true-false things.
So real numbers.
Real numbers. It introduced the concept of weighted inputs, allowing the network to decide which piece of information was more important, and also bias, which acts like a tuning knob for its activation threshold. It really felt like a machine that could learn.
It sounds incredibly promising, but this is where the limitations started to show up, right? It was a shallow network, and that turned out to be its Achilles heel.
It was indeed. This was the first major structural limitation, and it led directly to the first major AI winter. A single-layer perceptron was fundamentally restricted to handling functions that are linearly separable.
Okay, hang on. If I'm not a mathematician, what exactly does linearly separable mean for a system that's trying to learn?
It's a simple concept, really. Imagine you have a scatter plot of data points, say a bunch of blue dots and red dots.
Okay.
If you can draw one single straight line on that plot to perfectly separate all the blue dots from all the red dots, then that data is linearly separable. The perceptron could solve problems like or and logic because those are simple separations.
I see. But I'm guessing most real-world problems aren't that simple.
Not at all. The vast majority of real-world data, images, speech, complex concepts, they're all tangled together in a highly complex, nonlinear way. You can't separate them with one straight line. You need curves or multiple boundaries, or maybe even to view the data in a higher dimension.
Right.
The famous counterexample was the XOR function exclusive OR. It's ridiculously simple, but a perceptron just could not solve it.
So even though researchers introduced the idea of multi-layer perceptrons to handle this, they ran into other problems.
Crippling problems. This was in the 1960s and 70s.
Yeah.
Immense computational complexity, the need for gigantic amounts of data that simply didn't exist, and training times that were prohibitively long for the hardware of the day.
So the idea of depth existed, but it was just completely unusable. Research just hit a wall.
It went into a severe recession. That was the core of the first AI winter. And critically, during this time, researchers flocked to alternative machine learning methods that actually worked with the resources they had.
And the big one was the support vector machine, or SVM.
Yes. The SVM was the greatest competitor. It dominated for over a decade, through the 90s, because it was just so much more efficient. It required way less computational complexity and, most importantly, minimal data.
Which was key back then.
In a world starved for data, an SVM was superior. It focused only on the points closest to the decision boundary. It achieved great performance where deep networks couldn't even get off the ground. The neural network field was, largely left in the research wilderness until these fundamental problems could be solved.
This brings us to what I think is maybe the single biggest conceptual breakthrough of the whole deep learning revolution. The thing that separates it entirely from classical systems like SVMs, the idea of feature representation.
This shift in how the system looks at the data is really the core intellectual revolution here. Before deep learning, the performance of any model was entirely dependent on human experts engaging in this intense, complex process called feature engineering.
That sounds like an exhausting job. Can you break down what that actually involved?
It meant that for the machine to learn anything, a human expert who deeply understood the domain had to manually decide and then define the relevant characteristics, the features that the model should use.
So let's use that cat example.
Perfect example. In classical machine learning, this manual process was a huge bottleneck. The expert would have to write code specifically designed to find cat-like characteristics, detect two pointy objects near the top of the ears, those are the ears, calculate the angle between two lines, that's the eye shape.
You're literally telling it what a cat looks like, piece by piece.
You, the human, designed the entire input pipeline. You were telling the algorithm exactly what to look for. And that system was incredibly brittle.
Right. If the cat was turned sideways, or the lighting was different, or it wasn't perfectly aligned with those rules you wrote,
the whole system failed. You couldn't generalize it. And if you wanted to detect a dog instead of a cat, you had to go back to square one and manually redesign a whole new set of rules for dog features.
it just couldn't scale.
Not at all. And this is where deep learning fundamentally automated this whole process, giving rise to this concept of representation learning.
Okay, so what defines representation learning?
Deep learning models are really defined by this capability. Instead of a human predetermining the features, the model uses its multiple nonlinear layers to automatically transform the raw input, say, millions of raw pixels, into increasingly abstract and useful feature representations all by itself.
So the network isn't told to look for ears, it just looks at the raw data and starts figuring out that certain combinations of pixel gradients reliably correlate with some higher level concept.
Exactly. That's the hierarchical structure at work. The network essentially teaches itself. The very first layer might learn extremely low-level things like simple edges and specific color gradients.
The basic building blocks.
The basics. The next layer takes those edges and learns to combine them into corners or curves or textures. The third layer recognizes more complex components like eyes or ears by combining those textures and shapes.
And then finally, the highest layers combine all those components to identify the overall object, the cat.
And that ability to automatically learn features, abstracting complexity across multiple levels, is what made deep learning so generalizable and so robust.
Which directly explains the need for depth. If you need to build that hierarchy, going from pixels to edges to shakes to objects, you simply have to have many stacked layers to do all those transformations.
That's absolutely right. And this is where the limitations of those early shallow networks become so clear. A shallow network would require exponentially more parameters to represent the exact same complex function that a deep network can handle efficiently.
So trying to map raw pixels directly to the concept of CAD with just one or two layers is just statistically impossible.
It's absurd. And that leads us to this technical term that you often hear, the curse of dimensionality.
Right. That sounds bad.
It's a statistical nightmare. It just means that as you increase the number of features or dimensions in your data, and raw images have thousands, the volume of the input space grows exponentially. You need an exponentially larger amount of data just to cover that space.
So a shallow network would need a ridiculous number of parameters and an unrealistic amount of data to overcome this curse.
Exactly. So depth isn't just about being bigger, it's about being mathematically efficient. By breaking down the complex problem into these small, hierarchical, manageable steps, the deep network uses its parameters so much more effectively than a shallow one trying to do the whole job at once.
That realization that depth provides an efficient representation was the key. But, knowing you need depth is one thing. Actually being able to train those deep networks was the next giant hurdle.
It was.
We knew depth was necessary. But as you said, the first AI winter proved stacking layers was computationally infeasible. So let's talk about the algorithmic innovations that finally allowed us to train them, starting with the core engine, the backpropagation algorithm.
Backpropagation, or BP, is often seen as the primary mechanism that brought neural networks back from the dead in the 1980s. It's what allows the network to learn from its mistakes, even across many, many layers.
How does it manage that error correction in such a complex system?
It works in two phases. First, you have the forward pass. Data goes through the network layer by layer until it spits out a final prediction. Then we use what's called the loss function to calculate how wrong that prediction was, the overall error.
And then comes the magic of the backward pass.
Yes. The backward pass takes that error signal and propagates it backward from the output layer all the way back to the input layers. It uses the mathematical chain rule to precisely calculate how much every single weight in the entire network contributed to that final error.
So it figures out who to blame for the mistake.
It gives you the error gradient, which tells you two things for every weight: how much it contributed to the error, and in which direction you need to adjust it to make the error smaller. It gives you a roadmap for correction.
And this is what allows a network to slowly get better with each example.
It is. It's remarkably effective for calculating those gradients. But when researchers tried to apply this powerful tool to truly deep networks, say 10 or 15 layers, they immediately hit a fundamental optimization crisis, the vanishing gradient problem.
Can you give us an analogy for how that gradient signal just evaporates?
Yeah, think of the gradient as the learning signal. It's the volume of the lesson. When you use the chain rule to send the signal backward through dozens of layers, you're multiplying many small numbers together.
Okay.
If each of those layers reduces the magnitude of the signal slightly, say by multiplying it by 0.5, and you do that 15 or 20 times, the signal just decays exponentially.
It's like a compounding decay. If you start with a learning signal of 100, after just a few layers, it's practically 0.
Precisely. So the early layers, the ones responsible for learning those crucial foundational features like edges and textures, they receive a vanishingly small error signal. Their weights never update, or they update so slowly they just stagnate. The network's foundation remains useless.
So overcoming this vanishing gradient was the single most essential algorithmic challenge to making deep learning possible. What were the technical solutions?
Well, the first major breakthrough was about getting the network started correctly. This was something called layerwise pretraining, innovated by Hinton and others around 2006.
How did just initializing the weights better solve the vanishing gradient problem?
Well, initialization is critical. If all your weights start out identical, what we call symmetrical, then during the backward pass, every neuron in a layer will get the same update. The network just can't learn diverse features.
It stays stuck.
Right. Layerwise pre-training used unsupervised methods, training one layer at a time to learn useful features before connecting it to the next. This ensured the weights were set to a useful non-random starting point, which helps overcome the difficulties of training a deep network from scratch.
That gets you off the starting line. But what about the signal decaying during the race itself?
That was the second, and arguably more important, breakthrough: the shift in activation functions. For decades, networks use functions like the sigmoid, which squish the entire input space into a tiny range, usually between 0 and 1.
And that squishing is what causes the problem.
It's what generates the small derivatives, leading directly to the vanishing gradient. But the answer turned out to be much simpler. The rectified linear unit, or ReLU.
ReLU, so how does that work?
ReLU, which became popular around 2011, solved this elegantly. It just maps any input x to the maximum of 0 or x. So for any positive input, the gradient is simply 1. It doesn't squish the positive input space at all.
So it just lets the signal pass through unchanged if it's positive.
Exactly. And that simple property effectively ensures that the training signal, the gradient, can pass clearly and without that exponential decay through many, many layers. It was the functional change that made it possible to reliably train truly deep architectures.
So ReLU keeps the volume of the error signal strong enough to reach those early foundational layers, letting the whole structure learn together?
Exactly. And there were other initialization techniques too, simple mathematical rules for scaling initial weights based on the network structure. All these things together help stabilize backpropagation in these very complex networks.
Okay, so we have the theory for why we need depth, and now we have the refined algorithmic engine ready to go. But an engine is useless without fuel and power. That brings us to the hardware and data tsunami.
This is the context that explains why deep learning exploded when it did, despite the algorithms being refined years earlier. And we start with the fuel, massive datasets.
Right. Deep learning models are known for being parameter heavy. Why does having millions of parameters mean you need massive amounts of data?
Think of parameters, the weights and biases, as switches that the network needs to set correctly. If you have millions of switches, but you only show the network a handful of examples,
It's just going to memorize them.
it will. It'll just memorize the few training examples it sees, adjusting those millions of switches perfectly for those inputs. That's overfitting. It gets 100% accuracy on the data it's seen, but it fails miserably on anything new.
So you need enough examples to force the model to learn general rules, not just memorize specific answers.
Absolutely. The rule of thumb you often hear is that you need about 10 times the number of data samples as you have parameters. For decades, that volume of labeled data simply did not exist.
But then came the internet and social media, and suddenly there was this vast data repository.
That was the game changer, the explosion of digital data. And critically, we started to see the creation of huge, publicly available labeled data sets, the most famous, of course, being ImageNet.
14 million labeled images.
That was the essential fuel that deep networks needed to finally perform effectively, generalize well, and leverage their complexity without just overfitting.
The data volume was there, but the computational cost of training on all that data must have been huge, which is where the power source, the GPU revolution, changed everything.
This is the critical hardware piece. Training a deep neural network is basically an endless, repetitive cycle of intensely complex matrix operations, multiplying and adding huge arrays of numbers.
And a standard CPU is just not built for that.
Not at all. A CPU is designed for sequential processing, handling one complex task at a time very efficiently. It has a few very powerful cores.
But GPUs were for video games, right? For graphics.
Exactly. GPUs, graphics processing units, were designed for rendering graphics, which also requires massive parallelism, calculating the color and light for millions of individual pixels all at once. So a GPU has thousands of smaller specialized cores designed to do simple repetitive math incredibly quickly and in parallel.
So the GPU architecture was just a perfect match for the math of neural networks.
It was a perfect, almost unforeseen synergy. The pioneering work, especially from Andrew Ng's group around 2008, showed that by shifting this workload to GPUs, you got this massive parallel processing capability. What might have taken weeks on a CPU could suddenly be done in days or even hours.
That kind of speed up changes everything. It means researchers can iterate and try new ideas so much faster.
And that's what created the virtuous cycle. The availability of massive data justified the investment in powerful GPUs. The performance gains unlocked by those GPUs allowed models to use that data effectively, and that in turn spurred the development of even more complex, data-hungry models.
Creating a feedback loop.
A constant feedback loop between compute capability and model efficacy. Without data and parallel processing power coming together, the algorithmic improvements would have just remained a theoretical curiosity.
So it's the convergence of the three, the architecture, the algorithms, and the data and computation that finally lit the fuse. And this led directly to these huge, tangible victories in the real world. Let's talk about the triumphs of architecture.
The first major validation for all of this came in computer vision. using convolutional neural networks, or CNNs.
What makes CNNs so special for images?
Well, they're a specialized architecture inspired by the structure of the human visual cortex, and they're designed to process spatial data like images. They use convolution layers that apply filters to small areas of the input.
So it looks at a tiny patch of the image at a time.
Right, and this allows it to learn what we call translation invariant features. Basically, if a CNN learns to recognize an eye in the top left corner of an image, it can still recognize it in the bottom right corner without needing a whole new set of parameters.
That's very efficient. But the big moment, the validation, came with AlexNet in 2012.
That was the watershed moment for the entire field. In the 2012 ImageNet competition, AlexNet, a deep convolutional network, just blew everything else away. The previous year's best classical model had an error rate in the mid-20s.
And AlexNet.
AlexNet nearly half that. It got an error rate of about 15%.
Wow. That's not just an improvement, that's a complete paradigm shift. What was the reaction to that?
It was seismic. The jump was so huge, so undeniable, that the entire computer vision community realized almost overnight that their traditional methods were obsolete. It was definitive proof that deep learning, finally enabled by GPUs and ImageNet, was fundamentally superior for these tasks.
And that success just fueled more innovation, leading to even deeper models, like ResNet.
ResNet, or Residual Network, was another massive leap. It won the competition in 2015 with 152 layers.
152 layers. How did they avoid the vanishing gradient problem with a network that deep?
They used a brilliant architectural trick called the skip connection. It's basically a highway that lets the signal from an earlier layer skip over a few layers and get added directly to the output of a later layer.
So it's a shortcut for the gradient.
It's a shortcut that maintains the integrity of the signal. It ensures the gradient can propagate unimpeded across vast depths, allowing the network to learn the residual, or the difference, which is often easier. It just made it possible to train networks that were previously considered impossible.
So that covers vision. But sequence data, like speech or text, needed a different approach because context and time are so important.
Exactly. For sequential data, the initial work was all about recurrent neural networks, or RNNs. They introduced this concept of an internal state, or a memory, allowing them to process inputs one after another while keeping track of what came before.
But the basic RNNs had a major flaw, right? The long-term dependency problem. They couldn't remember things from far back in a sequence.
They were still highly susceptible to the vanishing gradient, but this time it was across the time dimension. If a sentence started 30 words ago, the RNN would often forget the beginning by the time it got to the end.
And the solution to that was the long short-term memory network, the LSTM.
LSTMs were ingenious. They introduced a dedicated internal memory cell, like a conveyor belt for information. But crucially, they added these regulatory structures called gating units: an input gate, a forget gate, and an output gate.
Let's zoom in on that forget gate. That seems key.
It is the heart of the solution. The forget gate's job is to decide what information to keep in the memory cell and what to throw away. It learns to manage context. For instance, to forget the subject of a previous paragraph when starting a new one, or to explicitly hold on to the subject of a very long sentence.
So it's actively managing its own memory.
Yes, and this mechanism prevents the signal from decaying over time, solving that long-term dependency problem. And LSTMs immediately led to huge breakthroughs in speech recognition around 2013, becoming the backbone of virtual assistants.
So CNNs took over vision, LSTMs took over sequences, but the landscape has shifted again more recently with the transformer model.
The transformer, introduced in 2017, was another fundamental architectural shift. It moved away from the sequential, one-word-at-a-time processing of RNNs and LSTMs.
And it did that using the self-attention mechanism. How does that work differently?
LSTMs still process data token by token. The transformer processes the entire input sequence all at once. The self-attention mechanism lets the network weigh the relevance of every other word to the current word it's looking at.
So if it sees the word it can look back across the whole sentence and figure out which noun it refers to.
Instantly. Even if that noun is 50 words away, it bypasses the need for sequential memory by building a direct map of all the contextual dependencies across the entire sequence at once.
Which must make it much more parallelizable for GPUs.
Exponentially faster. And that allowed the models to scale up dramatically, leading directly to the foundation for large language models like BERT and, of course, the GPT series.
It's just an incredible story of progress. But as we wrap up, I think it's really important to stress that deep learning isn't magic, despite what it can do.
That is the key takeaway. The success is the result of persistent, gradual, consistent technical refinement, addressing these decades-old challenges one by one. And one of the biggest challenges with these massive models is just managing the risk of overfitting.
The memorization problem. What techniques were crucial for managing that complexity?
Well, the development of robust regularization techniques was absolutely non-negotiable. Two of them really stand out: dropout and batch normalization.
Okay, let's start with dropout. How does randomly turning off neurons help prevent overfitting?
Dropout is a brilliant and simple idea. Think of training a neural network like training a large team on a project. If you let individual members or neurons specialize too much, the project becomes reliant on them. If one is absent, everything fails.
Right.
During each training step, dropout randomly drops out a percentage of neurons in their connections. It forces redundancy. If you know half your team might be absent tomorrow, you make sure every remaining member learns all aspects of the task. It forces the network to find multiple redundant pathways to a solution, making it more robust.
And then there's batch normalization. That seems more about stabilizing the training itself.
It is. Batch norm addresses something called internal covariance shift. As the weights throughout the network are constantly updating during training, the distribution of the signals coming out of the hidden layers changes wildly. It's like trying to hit a moving target.
So each layer is constantly having to readapt to a change in input from the layer before it.
Precisely. And that slows everything down. Batch norm solves this by normalizing the output of each layer, making sure the distribution of signals remains stable. This stabilization lets you use much higher learning rates, which speeds up training dramatically.
We've focused a lot on supervised learning, but these ideas extend beyond that, right? Into unsupervised and reinforcement learning.
Certainly. In the unsupervised world, you have things like autoencoders. These are networks used for feature discovery and data compression. They have a bottleneck structure that forces them to learn the most essential features of data just by trying to reconstruct it.
So they're great for things like removing noise from an image.
Exactly. And then there's deep reinforcement learning, which is what brought AI to games like chess and Go. It combines deep learning's ability to handle high-dimensional input, like a screen full of pixels, with the decision-making framework of reinforcement learning.
So it learns through trial and error, but using these powerful, deep networks to understand the state of the world.
Yes. But despite all this success, there are still ongoing challenges that remind us these models are not flawless.
And the biggest one is probably still data efficiency.
It remains a huge challenge. Deep learning is incredibly data-hungry. This is why techniques like transfer learning have become so critical.
Which is the idea of taking a big model that's already been trained on a general data set and then just fine-tuning it for your specific smaller tasks.
Exactly. You get the benefit of all the general features it's already learned, and you only need a small amount of specialized data to teach it the final step.
And finally, there's this really fascinating issue of robustness, which is captured by the idea of adversarial examples. This really makes you question how these systems understand anything.
It is unsettling. Researchers have shown you can take an image that a model classifies with 99% confidence, say a cat, and you can add a tiny amount of noise, a perturbation so small a human can't see it.
And the model's prediction completely changes.
It will instantly classify it as a school bus or an ostrich with 99% confidence. This suggests that despite being highly accurate, these systems are relying on features that are fundamentally different and more brittle than how humans perceive the world. Their reasoning is fragile, and that's a huge research frontier.
What an incredible journey from that theoretical promise in the 1940s through the AI winters to the convergence of algorithms, data, and computation that launched this revolution. It really wasn't one single invention, but decades of that persistent technical refinement.
That convergence really is the complete story. And this foundational discussion, it paves the way for us to explore the specifics in much more detail in the future. How backpropagation actually works, what's going on inside the gates of an LSTM, or how that revolutionary attention mechanism really works.
We'll definitely be circling back to those. It's fascinating to think that the next big leap might come not from inventing something totally new, but from that same slow, painstaking process of refinement that got us here.
Indeed. The pursuit of stability and efficiency is often where the true breakthroughs are hiding.
Thanks for listening to the Adaptix podcast. If you have any questions, feel free to reach out to us.